The device you're watching this on right now, it is an absolute marvel of engineering. But at its very core, it's made from one of the most common things on Earth, sand. So today, we're going to explore the incredible journey of how we taught simple silicon to think, creating the foundation for, well, our entire digital world.
So how do you take a handful of beach sand and turn it into a smartphone? I mean, it sounds like some kind of magic, right? But it's really a story of controlling electricity with some very, very clever chemistry. Let's dive in.
Okay, so the first piece of the puzzle was finding the absolute perfect material. We couldn't use something that just lets electricity run wild, and we couldn't use something that stops it completely. We needed something, just right. On one end of the spectrum, you have conductors, like copper. They're fantastic at letting electrons flow. Great for a power cord, but there's zero control. They're just always on. Then you have the other extreme, insulators, like the rubber wrapped around that cord. They block electricity completely. They're always off. For computing, for anything smart, we needed something in the middle. And that brings us to the hero of our story, the semiconductor. This is our Goldilocks material. Not too hot, not too cold. And here's the magic word. Its conductivity can be controlled. We can tell it exactly when to act like a conductor and when to act like an insulator. And the most famous semiconductor of them all? Silicon. Yep, the main ingredient in ordinary sand. And the reason we love it is because it's everywhere. It's so abundant, a single cubic mile of seawater has something like 15,000 tons of it. This cheap, plentiful material held the key to the entire digital revolution. But here's the catch. Pure silicon isn't enough. On its own, it's actually a pretty decent insulator. To unlock its true potential, we needed a kind of secret recipe. We had to add tiny, incredibly precise impurities to totally change its electrical personality.
See, in its pure crystalline form, silicon's atomic structure is this perfect, stable grid. Every atom has 4 outer electrons, and they're all holding hands tightly with their neighbors in what are called covalent bonds. It's all locked up. No free electrons means no electricity can flow. So how do we free things up?
This is where the recipe, a process called doping, begins. We mix in a tiny bit of an element like phosphorus, which has 5 outer electrons. Now, 4 of those 5 electrons bond perfectly with the silicon around them, but that 5th one, it's left over. It's a free agent, just wandering around, ready to move and carry a negative charge. We call this N-type silicon, for negative. Now, we can also do the exact opposite. What if we dope the silicon with an element like boron, which only has 3 outer electrons? Well, now we've created a gap, a vacant spot where an electron should be. We call this a hole. And this hole can move. An electron from a neighbor can jump in, leaving a new hole behind. It acts just like a moving positive charge. And this, you guessed it, is P-type silicon, for positive. Okay, so now we've got our 2 custom materials, N-type, which is full of extra electrons, and P-type, which is full of extra holes. So what happens when we stick them together? Well, that's when things get really interesting, because we can create our very first fundamental electronic component. We get a diode. By physically joining a piece of P-type and N-type silicon, we create what's called a P-N junction. And this incredibly simple device has one profound ability. It acts as a one-way gate for electricity. Current can flow one way, but it gets completely blocked if it tries to go the other way. The best way to think about it is like a spring-loaded gate in a water pipe. If water pushes from the correct direction, the pressure easily swings the gate open and the water flows right through. But if water tries to flow from the other direction, it just slams that gate shut even tighter, no flow. And that's exactly what happens with electricity in a diode. If we apply voltage the right way, we call this forward bias, it pushes the electrons and holes together right at that junction, and poof, current flows. The door is wide open. But if we flip the voltage, that's reverse bias, it pulls the electrons and holes away from the junction, creating an empty zone that blocks any current from getting through. The door is slammed shut.
So why is a one-way gate so important? Well, think about the power coming from your wall outlet. It's AC, or alternating current, meaning it's constantly flipping direction, back and forth. But all your electronics, your phone, your laptop, they need stable DC, or direct current, that flows in just one direction. A diode acts as a rectifier. It lets through only the forward-flowing half of the electricity, chopping off the other half. This is the first crucial step inside every single power adapter you own.
A one-way gate is seriously powerful. But what if we could build a switch that we could turn on and off? Not with our hand, but with another, smaller electrical signal. Well, taking that next step brings us to what is arguably the single most important invention of the 20th century.
Meet the transistor. Instead of just a PN junction, it's more like a sandwich, like an NPN structure. And this little 3-leaded device gives us two unbelievable abilities. We can use it as a near-perfect digital switch, or we can use it as an amplifier. The faucet analogy is absolutely perfect here. Think about it. A tiny, effortless twist of the knob, that's your small input signal, can control a massive, powerful flow of water. A transistor does exactly that, but with electricity. A tiny voltage on its middle lead can control a much larger current flowing through the other two leads.
All you have to do is apply a tiny little voltage to that middle base layer, and bam! You open the floodgates for a huge current to flow from the collector to the emitter. Take that tiny voltage away, and the gate slams shut. That's it. That is the light switch. That is the on and the off. That is the 1 and the 0 that our entire digital world is built on. And when you shrink billions of these switches onto a single chip, you get the mind-boggling power in your computer.
But wait, there's more. It turns out these amazing PN junctions don't just control electricity, they can actually interact with light. This takes us into the super cool world of optoelectronics.
And really, it's a two-way street. You can put electricity in to get light out. That's what an LED does. Or you can put light in to get electricity out. That's what a solar cell does. Both are powered by that same simple PN junction.
An LED is really just a special kind of diode. When you push current through it the right way, electrons jump across that junction and fall into the holes on the P side. Now, as they fall into that lower energy state, they have to release that extra energy. And they do it by spitting out a little particle of light, a photon. The more current you push through, the more electrons combine, and the brighter the light gets. Simple as that. So what about going the other way? Well, a solar cell basically works like an LED in reverse. When a photon of light comes from the sun and smacks into the PN junction, its energy can knock an electron loose, creating a free electron and a hole. And that generates a voltage. A solar cell is really just a giant photodiode with a massive surface area designed to catch as many of those photons as possible.
So when you think about it, it's pretty incredible. From simple sand, we figured out how to make two special types of silicon. From that, we built one-way gates and tiny electrically controlled switches. And with just those two fundamental building blocks, repeated billions and billions of times, we built everything from supercomputers to the phone in your pocket. It all comes back to these simple, elegant ideas. The only question is, what will the next fundamental building block allow us to create?